Okay, I just pasted the link in the chat, so I think we should wait 1 or 2 minutes.
Christian, don't forget to mute all the people that is not in the organization panel.
Yeah. Thank you. I will change the security settings.
Security settings, policy.
Pierre-Louis, there's
Yes.
a question on Discord if you want to check it while we wait.
Yes. Yes, we can do that. No, because I'm on the private, maybe I'm on the private. Yes. Yeah, I should go here. Yes. I have one philosophical question. Is this object taking the quotient of u by y in the topological sense? No. I don't think so. Set corresponding. Okay, I'll try to answer this offline because I cannot really figure out a good answer now. Okay, shall we start?
Yes.
Okay, so we resume the second half of today's course, and as yesterday, I will start by giving some indications about exercises that are in the PDF. So I focus on 4, 5, and 6, and because time is I'm running a bit behind time, I will not be over detailed. So I will start with exercise 6. And we'll give a few details. Okay, so we have two families of types P and Q that are indexed over the same type A, and we consider the family again indexed over the same type A, whose component at X is Px arrow Qx. And the goal of the exercise is to express the transport for this new family R in terms of the transport for Q and the transport for P. And the formula is here. Okay. And okay, so the only thing that I'm going to do is the type checking to make sure that this is correctly typed. Okay, so let's do it. So what does it mean to transport relative to R along a path P? So the path P here will be the same here, and well, not here, it will be P minus 1, but it is always a path in A. So this path is from X to Y. Okay, and then this F, okay, this F, according to this hand side here, should be an element of, because P is from X to Y, this F should be an element of Rx. Okay, but this is what is written here, because F is supposed here to be from Px to Qx, which by definition is Rx. So this is correctly typed. And then we know that this after transport, so when we are here, we know that the result of the transport is in Ry. Okay, so because Ry is is Py arrow Qy, I can apply it to an element U of Py, which is written here, and I get an element of Qy. Okay, so we know that all this returns an element of Qy. Okay, so now let's see whether we get the same type by reading the right-hand side. So here we start from here. So we know that our U is of type Py. Okay, and this is why we now use transport along the inverse of Pi, because we want to move from Py to Px. Okay, this is what this transport does. And then this guy is in Px. Now I can apply F to this guy. Then we know, because F is from Px to Qx, we know that this guy is in Qx. And I can transport it along P with respect to the family Q, and I get somebody of type Qy. Okay, and why does this hold? Okay, because we have to prove it. We prove it by path induction, and path induction tells us that we only need to care for the case where P is refl. Okay, but we know that when P is refl, also P minus 1 is refl. Okay, so everything here boils down on the left to this guy boils down to F. So here we get F applied to U. Okay, now here everything boils down to U. Then I take FU and I take transport, trivial transport of FU, which is again FU. So you see that this holds. Okay, so this is how to prove exercise 6. And for exercise 4 and 5, it is a little bit more tricky, so I won't give you much detail. But I really recommend to do these exercises because they will force you to use recursion induction on simple types and make sure that you understand the mechanics. Okay, so that's why I insisted in including these exercises. So the two exercises propose a coding, an encoding of the coproduct and of the product in terms of the booleans. So it's quite nice to see that and boolean, sorry, and the sigma and pi types. Okay, so maybe it's enough if I give you the intuition, and yes. Okay, so the intuition here is that A plus B, okay, can be defined by, so what is rec 2 UAB? Well, it's a function from 2 to the universe, which in case it is applied to 0 returns A, and in case it is applied to 1 returns B. That's exactly what this function is. And so you see that it really encompasses the idea of a coproduct, because well, it's somehow a definition by case. It's a function from booleans to the universe. In case a boolean is true, then it's A. In case it's false, it's B. And for A times B, it's more or less the same idea. Except that it's now a pi type, okay. But with the same explanation, it will because 2 has 2 elements, okay. It's a function from intuitively, it's a function from 0, 1 to U. No, this is not terribly helpful. Why is this going to be the product? Yes, yeah, of course. Sorry, a function from 0, 1 to some type A is a pair of two elements of A. Okay, but this pair will be inhomogeneous because rect2 UAB, as I just said, returns A or returns B according to whether the value is true or false. So the pair here, your A is actually more like the universe, and your pair, the first element of your pair will be of type A, and the second element will be of type B. Okay. Maybe this is not very, very clear, but I will not give too much more details here. No, I will not. I will. I really recommend you to read the solutions, which are not complete, but they show you how to really encode not only the intuition, but also really how to encode recursion on the coproduct and the constructors of the product by means of these encoding. So let me not do it because I'm running a bit late, but I highly recommend you to work on that. Okay. Okay, so where were we? I think I stopped here. Yes, I stopped here while being continuous in my treatment. So I didn't prove this the content of this slide. So let me start from here again. So what this slide says is that maybe I recall because there was a break, so you might have forgotten. A type is a proposition if you can prove that for every pair of elements of this type, the equality between these two elements holds. You have a proof that X is equal to Y for all inhabitants of A. So now what we want to prove is that if all Bx are propositions, regardless of what A is, could be any type, then this guy is a proposition. So how do we prove this? Well, we have to prove that taking arbitrary elements F and G of this type, they are equal. By function extensionality, what we have to prove is that Fx is equal to Gx for all x. Okay, but where does this equality live? It lives in Bx, but Bx is a proposition. So this holds trivially because Bx is a proposition. Hence, it holds for all x. Hence, F and G are homotopic. Hence, they are equal by function extensionality. So you see, this proof is quite simple. Okay, then I discussed briefly Curry-Howard, and then I discussed this slide in some detail, so let me not repeat it. I just want to clean it. Okay, so we have a whole hierarchy of types, which says, well, essentially what it says is that when something is, when you can prove that something is an N type, it means that it has some structure of some dimensions up to N, and then after level N, everything is trivial. There is no more information. The information is lost. Okay. Good. So, for example, okay, and then I said, I pretended that we can start even at level -2 here because we have this fact here. Okay, but we will come to that later. Okay. So, first thing I want to do seriously is to connect rigorously, mathematically, the notion of contractible and the notion of proposition. So we have this theorem, which is nice, which says that the three following characterizations are equivalent. First one, a proof that A is contractible. Second thing, to have both a proof that A is inhabited and a proof that A is a proposition. And finally, a proof that A is equivalent to 1. Okay. So that gives you an idea of what a contractible type is topologically, especially the last one. Topologically, the last one says that because equivalence means equal up to deformation in topology. So it means that your space can be really contracted to 1, and what is 1 is the space with just 1 point. Okay, so the idea of contractible, as I said before, is that it can be contracted all to the point. So typically, this guy is not. The torus is not. You cannot contract it. You have a hole in the middle. You certainly cannot contract it to point. And there are many other examples, of course. Good. So how do we prove this? Well, we will need two little facts. Okay. The first fact is that 1 is a proposition. Okay, and we proved it without saying it earlier. Because, well, a long time ago, yesterday, I gave you a characterization of the type equals 1. And there were steps in this proof. And one of the steps consisted in showing that there is an inhabitant of this type, box 2. But this is exactly saying that, yes, this is exactly saying that 1 is a proposition, that you can prove that this type is inhabited, hence it exactly says that 1 is a proposition. Okay, so we know that 1 is a proposition, we have proved it already. Yes, so we will use that. And then there is another fact which I don't want to prove now because the right setting for proving it will come later. For the moment, we will admit it. If we know that 2 types are equivalent, and if A is contractible, then we can show that B is contractible. Okay, so actually, we don't need an equivalence, we just need a retraction. But we don't know yet what a retraction is. So I defer the proof of B, but I will use this fact. Okay, so so we are going to prove it, but let me make a remark. Because of this theorem, if we want to show that a type is a proposition, okay, then it is enough to prove that it is contractible. Yes, it's not written very clearly. To prove that A is a proposition, it is enough to assume that it is inhabited and to show that under this assumption it is contractible. Okay, this comes easily as a consequence of these 3 statements. And this way of proving that A is a proposition, since it's used over and over again, I give it a name. I call it the trick for proving that it is a proposition. I call it the is-prop trick. So when I will refer to the is-prop trick, it's exactly this. In order to show that something is a proposition, I will find I will find myself in a context where I know already that it is inhabited for some reason, and then I only have to show that it is contractible. Okay, because of this equivalence here. So let's prove now that contractible implies being a proposition and being inhabited. So this is completely trivial. If it is contractible, then it has a center, so it is inhabited. And then, because of the center, if we take any two elements, x, y of A, then I have a proof that x is equal to A, and I have a proof that A is equal to Y, okay, because of course we know that equality is symmetric. So by transitivity, I have a proof that x is equal to Y. Now, how do we prove 2 implies 1? So suppose that I'm a proposition and I'm inhabited. Why am I contractible? What did I write here? 2 implies 1. I think I wrote something that has nothing to do with the proof. So let me do it. We have to, if it's inhabited, then I will pick this inhabitant and decide that it is the center. Okay, and then it's certainly contractible because being a proposition, in particular, every element, every pair of elements. So if I take the first element to be A and the other element to be arbitrary, I know that they are equal, and this is what contractible means. Okay, so this is, I don't know what is this nonsense here. Okay, 2 implies 3. 2 implies 3. We have to prove, this is more interesting. We have to prove that there is an equivalence between A and 1. Okay, so we have to exhibit 2 maps from A to 1 and from 1 to A. Okay, but this is quite easy by the trick of taking constant functions, because both are inhabited, A and 1. So I can take, for going from A to 1, I can map every element of A to the unique element of 1, which is star. And if, on the other hand, I want to go from 1 to A, because A is contractible, it has a center, and center A, okay, an inhabitant, which I call the center. And I can take the constant function that maps everybody from 1 to this small a. And it's easy that, well, I don't have to do anything else. Why? Because this shows that they are logically equivalent. But they are both propositions, because we already know that yes, we are doing 2 implies 3. So we already know that A is a proposition. We know that 1 is a proposition. So these 2 guys are propositions. In order to show that they are equivalent, we just need to show that they are logically equivalent. And this is done trivially here. And then 3 implies 2. Okay, so if I have such an equivalence, we need to show that it is a proposition, it is inhabited. Okay, no, yes, but actually what I prove is I'm using B, okay? So I know that 1, okay, sorry, I need probably to show that 1 is contractible. Yes, I know that 1 is contractible. Why? Because I already know that 1 is a proposition and 1 is inhabited. It has star as an element. So 1 satisfies 2, and hence it satisfies 1, because we already proved the equivalence. Okay, so we know that 1 is contractible, and hence A being equivalent to 1 has to be contractible by this fact here. So end of the proof of these characterizations. Okay, so next thing, which is interesting is that we are going to show that every proposition is a set. Okay, and this is a special case of something that we will see a bit later. Namely, we will show that, yes, we'll show in general that if a certain type is of an n type, then it is also an n+1 type and an n+2 type. Okay, so the idea is that being, let me repeat this, being an n type means that you don't have any interesting structure above some level. So if you don't have interesting structure above level 3, for example, then of course, by just by the way of saying this, it will have no interesting structure at level 6, okay, above 6. So a fortiori. So this is why intuitively you have this commutability property. There's a typo here. Of H levels, but let me prove this in this case. Okay, we will prove that every proposition is a set. Okay, so suppose A is a proposition. So we have a function that applied to x and y gives a proof that x is equal to y for all x, y. And we need to show now that each of these, we want to show that it is a set. So we want to show that all these types here are propositions. But we are under the assumption that x is of type A and y is of type A. So we are under the assumption that A is inhabited. So we can use the trick which I mentioned, and we will show actually that x equals y is contractible. And we will look for a center and for a contraction. Yes, I didn't mention this name, but in the definition of contractibility, yes, so I say that this is a center, and I say that the function that goes together with the proof, well, together an element here is a center together with a function, and this function, I call it the contraction, okay, because it is the function that witnesses that it is really a center. Okay, so what we need is to find a center under contraction. Yes. Okay, so we look for a center under contraction to show that this guy is contractible. Okay, so how are we going to do this? Okay, so there's a little work to do. This proof is not trivial. It's not very difficult, but it's not trivial. So we have to tell a little story. So let's start this story. We can fix some z in A, okay, because well, it could be x or y, but we know that it is inhabited because we have these assumptions. So we fix some z, okay, because I don't want to say I fix x because yx, it could be y. So I fix z, okay, there is one, I know. And I'm considering now the family of types. Cu is the type pi u z equals u. Okay, so it takes every element u to a proof that z is equal to u. So this is a family of types, and we have seen in earlier properties of transport that we know that the transport relative to this family along to a path P of a path Q is the concatenation of Q and P. Okay, so it type checks and it works. So we will use this. Okay, now let's consider now the function. So remember that we have this function f, and let us fix our z. So we already fixed z, and let us consider the function that maps u to f of zu. Okay, so we notice that this function has the type PUCU. Something is a bit strange here. It maps, yes. Maybe there's a typo here. Is there a typo? So what is the type of G? The type of G, okay, it takes a U of type A, good, and maps it to f of zu, which is a proof of x equals. This is a proof of z equals u. Okay. So my impression is that the CU is just, sorry, this is clearly, there's no pi here. Yes, the family C is just at each U, it's just this equality type. Okay, and then this type checks. The function G has really the type PUCU. Okay. Hence, we can what we can do. We can apply. Yes, we can use. We have this path P, which is between x and y here. Yes, so we can apply it. We can apply G to it. So it's going to be an equality between G of x and G of y. Okay, but because of transport and things like that, actually what happens is that you have to do a little bit of transport, and this transport here reduces to concatenating G of x with P. Okay, let me just type check this to make sure that at least this type checks. So P is from x to y, and G of x okay, G of x is of type Cx. Okay, it's from so Cx is x equals u. So you have a proof that x is equal to u, and you have a proof that x is equal to y. Okay, so this does not type check. I should have put the P somewhere else. Okay, so let me write it, because I apparently confused things here. So G, let me write everything. So G of x is f of zu. G of x. G of x is f of G of x is f of zx. So it's a proof that z is equal to x. I think it was right. It was right. And then P is a proof that x is equal to y. Okay, and G of y is oh, this is the point, by the way. So G of y is f of zy, which is a proof that z is equal to y. So you see that if I concatenate these two, I get the path from z to y, and well, it's really not difficult to prove by properties of transport that that applying in a dependent way the function g to the path p provides a proof that this equality holds. hence, we can, by inverting paths, we have a proof that P is equal to G of X minus 1 concatenated with G of Y, because I can, of course, concatenate on both sides by G of X minus 1. Here this cancels, so I get P, and here I have G of X minus 1 concatenated with G of Y. And this is very interesting because these guys here are fixed. X and Y are fixed from the beginning. And P was any path here. So what we have shown in one shot, we have shown that this element here, which is a special element in X equals Y, is a center. And I also have the contraction because I have proved that for every other P, it is equal to this particular element. Okay. Hence, I have proved that X equal Y is contractible. Okay. So remember, we have proved that X equal A, Y is contractible. Hence, it is a proposition. Okay, so I'm sorry because there was some bit of confusion in a typo which perturbed, was a bit disturbing, but the proof works. So let me draw a parallel here for those of you who know a little bit of category theory. Okay. So this is a parallel only for those who know a little bit of category theory. So in category theory, you have something called monoidal categories. And in monoidal categories, you have something called a coherence theorem. Okay, so I won't be very detailed on what it means, but it says essentially that all diagrams commute. So all diagrams commute mean that you have different morphisms called canonical morphisms that go from one point to the other. So that could be one way, and that could be another way to go from here to here. And the coherence theorem says that in a monoidal categories, all these guys are the same. And how do you prove it? You prove it by using some kind of rewriting system where you prove that these two objects go to the same normal form here, which depends only on these two objects. And then you show that there is a morphism which depends also only on this object, and a morphism here that also depends only on this object. And these morphisms are invertible. So you have a canonical path from this guy to this guy, and then you prove that P is equal to this canonical guy and that Q is equal to this canonical guy, and hence they are equal. And you see that this canonical guy looks very much like this formula here, because it is going down and then up. So taking some path and then the inverse of the path. And you see that, so here there's a striking parallel. This is like X, this guy is like X, this guy is like Y, okay? And then this guy is like G of X minus 1, and this guy is like G of Y. Okay, so it's just a suggestion that this proof technique is very familiar in similar settings, because coherence theorems are really about not having too much higher structures, okay? Because it says that all these guys are equal. Okay, so every proposition is a set, and you see that the proof is not trivial. You have really to work a little bit to find the proper argument. Good. What other things can we say? we can say that the type which says that a type is contractible, or the type which says that a type is a proposition, is itself a proposition. So what we can say is that for all, if you prefer, we can say that for all A, we have that is prop of is contre of A, or is prop of A. Okay. For all type, of course, you don't have is prop of A, only for the propositions. But for all type, you have is prop of A. Okay. So how do we prove this? So it's two separate proofs for is prop and for is contre. So we want to prove that if two elements Fg are inhabitants of is prop of A, so they have this type. We want to prove that they are equal. That's our goal. Okay, so in order to prove that they are equal by function extensionality, it's enough to prove that by applying them to all xy, we have f of xy is equal to g of xy. Okay, but we have assumed that there is an f in this type, which means that we have assumed that that A is a proposition, okay? Because we have assumed that this guy is inhabited, okay? So we know by our assumption that A is a proposition, but we already proved that every proposition is a set. So we know that A is a set. Therefore, by definition of a set, we know that all these types here, x equals a, y, are propositions. And because they are propositions, then in particular, all these equalities that we need in order to show that f is equal to g, they hold, because this is a proposition. Hence, f are equal to g, and hence, this type is a proposition. Okay, so how do we do is contre? We need to show, so we can use induction on sigma types. So we have to show that if I give you two arbitrary elements in is contre of A, so one will be A pi, and the other will be A prime rho. So for all such pairs of elements, okay, so A is a center and pi is a contraction relative to the center for and what? Yes, and A prime is another center and the rho is a contraction for this center. We have to show that they are equal. Okay, but we know what is equality on sigma types. So we have to find a proof that A is equal to A prime. And we also have to find a way to prove that pi is equal to rho up to some transport, which is here. So we have to prove these two equalities here. We have to prove, well, we have to exhibit Q, and we have to exhibit a proof of this. Okay, so how can we get a proof that A is equal to A prime? Okay, that's not difficult, because with my assumptions, I have my pi, which is a contraction, so I can apply pi to A prime. If I apply pi to A prime, I get a proof that A is equal to A prime. So this is good. I've got one. And then we have to show that these two guys are equal. Okay, by function extensionality, it's enough to show that applied to Z they are equal. Okay, but wait a minute, this equality happens in this type. Okay, but our assumption was that, no, sorry, by assumption, yes, by assumption, since we have this, since we have A and pi, we have by assumption that A is contractible. Hence, it is a proposition. Hence, it is a set, because we have shown that contractible implies proposition, proposition implies set. And again, as we did before, we know that this type, by definition of a set, we know that this type is a proposition, and hence we don't even need to know what this guy is and what this guy is. Whatever they are, they must be equal. End of the proof. Okay, so these proofs are quite easy, okay, but you have to think well before writing them. This proof, I find it really a bit more difficult because you have to get the idea of finding this center here, which I think is clever. I mean, if you somebody who has not seen this before, it's a bit more difficult to find it. Okay, so let's see other properties. Yes, so this is a trivial slide, but it's interesting. So it says that if P and Q are contractible, then they are logically equivalent. They are always logically equivalent, and moreover, they are equivalent. Okay. Why is it so? Because well, because they are not empty, because they are in a contractible type is inhabited. Okay, so you can define a function from P to Q. Okay, we have done this before, the constant function that goes to the center and reciprocally. So we know that they are logically equivalent, and we already know that logical equivalence for propositions is the same as equivalent. So they are also equivalent. Okay. And also all functions that go from P to Q have quasi-inverses. Okay, so if and more precisely, if I take any pair of function f from P to Q and g from Q to P, okay, they are automatically quasi-inverses for the good reason that P and Q are propositions, but this we already have seen. Okay, so here are two very important and interesting properties, and we will use them later. So let me state the two properties. The first one says, so it's about a type family indexed by some type A. And suppose that all Px are contractible, then the total type sigma x Px is equivalent to A. Okay, so here is a naive proof. Because Px is contractible, it's essentially one point. And then this, you know, it's a disjoint union of all the Px. So you take 1 point set, you take a 1 point set for each element of A. So you take a coproduct of copies of singletons, or copies of 1 for cardinality A. And this should be A. Okay, that's a naive set theoretic view. And now we need a proof, of course, but I will give it after. And then the second statement is a bit different. So we have the same family, but the assumption now is different. It is A that we decide to focus on, and we say that we suppose that A is contractible with center A0. Then sigma x P of x is equivalent to P A0. So if you remember that in a contractible type, actually every inhabitant is a center, then this says that whatever element, you can pick an element in A, your favorite element, then this whole total space is equivalent to just the fiber at A0, P of A0. Okay, so let's prove the two, knowing that this is harder than this. Okay, this will need 2 slides, well, 1.5 slides. This just needs a few lines. So let's do the first. So, okay, so we know that each Px is contractible. So we can collect, yes, we know we can choose the center in each Px and collect this information, and we get a function from of this type, okay, which takes each x to a center of Px. Okay. Hence, we know, so this function, I call it center. And what I require, what I notice, well, the property of this function center is that yes, because P of x is contractible, if I take any x and any y in P of x, I will have a proof that y is equal to center of x. Okay, because it is by contractibility of P of x. Okay, center of x being the center for P of the chosen center for P of x. So I have all this information. I have this function, and I know that I have a proof of this for all x and y. So now we need to find functions that go from here to here and from here to here. So the first function goes, well, we know it already. It's the first projection. We have already worked on it. And for the other one, we can map an element of capital A to the pair of x and center x. And it's not difficult to find out that they are quasi-inverses. So this proof is without any, you don't need to think hard. It's really a simple one. The other one is a bit more tricky. So let's do it first in the non-tricky way. And then we will see that it doesn't quite work. So there are two natural functions that you can think of. So we now need now we need to relate this type to this type. So we want to go from, so the assumption is that A is contractible with center A0. So we start from an element of P A0, and we want to get an element here. So we start from B, which is of type P A0, and we map it just to the pair A0B, because B is being in P of A0. This pair is a nice element of this type. So here, nothing fancy. It's a very easy function. And for the other way around, we have to think a little bit more. So suppose we have a pair AB. So it means that this B here lives. This B is of type PA. Okay, but we want some person in PA0 because we want to go to PA0. So what we need to do is to transport this element B, okay, so that it belongs to PA0. Okay, but we have a proof that A is contractible. So this is witnessed by this function f, and this function f tells me that f applied to A is a proof that A0 is equal to A, or A is equal to A0. Yes. I don't know why I put a -1 here. This is strange. This FA. How did I define contractible? Yes, the center is on the left, so it should not be a -1. Should not be a -1 here. Yes, so here it should not be a -1. Because let me repeat, f of A is a proof that A0 is equal to A. Okay, so if I no, sorry, this was correct. This was correct. So f of A is a proof that A0 is equal to A, and B is an element of P of A. So if I invert FA, I have a proof that A is equal to A0. So I can transport this B to belong now to P of A0. And this is exactly what I'm doing here. I'm transporting B relative to the family P along this path that goes from A to A0. So this guy is certainly in PA0. So this is well typed. Okay. The problem here is in proving that these are two inverses. So one direction is easy. Okay, so we can do it. We can do it right now. So if we start from an AB, so if we start from this type here, and we apply first this function. No, sorry. If I what? Yes. So I start from here. Okay. So I apply this function. So I get this term here. Okay. And then I apply the other function. So I will get the pair A0, this guy. So this is written here. So this is one composition of these two functions, and we have to prove that they are equal. And this is okay. This is okay because it follows by the by the characterization of the equality on sigma types. Okay, we need a proof that A is equal to A0, but this is just FA. And transport is exactly the equality between these guys works by definition of transport. So there is no big deal here. No. Maybe this is the hard direction. So let me check on the next slide. So the point here is that when we choose a center, so maybe I should go here. When we choose, when we have a witness that something is contractible, so we have a certain AF of type is contra of A. So we know that for all x, fx is a proof that A is equal to x. Okay, but nothing tells me that this function, when applied to A, is the reflexivity. And this can be a problem in proofs because well, most of the time when we produce a proof of is contra A, the function f will have this property because this will be proved by path induction, and usually we will have this by construction. But if we start from any element of is control A, we cannot assume that. But we can observe that if we have chosen some f that does not satisfy that fa, so fa is not necessarily ref A. But we can make some kind of change of base. So suppose I have a function f. Okay, I can define a new function out of f, which is this function here. It's written here. So I have a new function. Let me call it f prime, which takes an element a, okay, and return fa prefixed with the path fa0 minus 1. And this new function f prime will satisfy this requirement. So we will, if I take this function and I call it f prime, okay, we will have that f prime of a0 is, well, by beta conversion, this fa0 minus 1 concatenated with fa0, hence is ref a0. So we can always manage to find a pair AF such that f of A is ref of A. Okay, for the center, for the chosen center. Okay, well, propositionally, not definitionally. Okay, so we keep this in mind. The next thing is to observe that, yes, next thing is to observe that we already know that if we take, when we do transport, we know that by definition, if P is definitionally equal to ref, then the transport of B along P is exactly B definitionally. So we want a weaker version. We want to show that as soon as the path is propositionally equal to the reflexivity, then transporting along this path is doing nothing up to propositional equality. So technically, we want to show that for each type family, for each x, okay, if I have a path, a loop from x to x that happens to be equal to ref of x in the propositional sense, then when I do transport along this path, I have also the propositional equality that transport PB is equal to B. Okay, and this is easy. Again, you do a path induction applied to this type. Okay, so with these two observations, no, there's a third observation here. So let's look at this first observation. Okay, yes, it's another easy observation. If you can prove that a path is propositionally equal to ref, then the inverse of this path can also be proved to be propositionally equal to ref. Okay, so why is this the case? Well, just simple manipulation. You start, so you have to prove that reflex is equal to P minus 1. So you start from reflex, but you know that by the law of inversions, the group laws, we know that for any path, you have P minus dot P equals ref. Okay, but we already know that P, that's our assumption that P is ref. So P minus 1 concatenated with P is P minus 1 concatenated with reflex, and by the identity laws, this is P minus 1. So it's easy manipulation. So let's now take profit of these three observations. And what do we need to show? Well, we need to show exactly what was written here, by the way. So we need to show, that's the hard part of the proof. We need to show that if we start from PA0 and do this function, and because this is what is written here, yes. Yes. Okay. So this is what we get. We start from B, and we have to show that it is equal to this guy. And now things are easy because we have chosen FA0 to be equal to reflexivity. Hence, we know that the inverse is also equal to reflexivity by point C. Then we know that the transport along this path is equal to B by B. And we have used A because we have used the fact that FA0 is equal to the identity. So you see, we have used the 3 points, and the proof is the proof is over. But you see that we had to take a little bit care of how we use the information that A is contractible. Not any witness of A being contractible allow us to finish the proof. So this is why you needed some preparations. Okay, so let's continue with other properties. So I promised you to define the notion of retraction. So a retraction is somehow the half of an equivalence. So a retraction is a function that comes together with another function. So it starts really like an equivalence, but you require only that R composed with S is homotopy to the identity, not the other one. Okay, and this is called a retraction. Okay, and usually we call one is called a section. Which one? The S probably. The S is a section. Yes. 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 B is a smaller guy on which you retract, and S is some kind of section that maps B to the larger one. Okay. So anyway, this is the definition of retraction. And the property is that once you know that A is contractible and that B is a retract of A, then also B is contractible. So proof. Suppose that we have a witness that A is contractible. So we have a pair A0F, and we want to show that B is contractible. So the first step is to choose the point in B. And the function R provides me with an element, which is R of A0. So my goal now is to prove that everybody in B is equal to R of A0. So I need to build a proof that R of A0 is equal to Y. Okay, but because I have this witness here of contraction, I can apply. So this Y is arbitrary. Okay, from B, I can apply S to B because S goes from B to A. So I can do S of Y, and then I can apply F to S of Y, which will provide me with a proof that A0 is equal to S of Y by contractibility of A, of capital A. Then I can apply the function R to this path, okay, which will give me a proof that, so let me write it, this guy here is a proof that R of A0 is equal to R of S y. Okay, but I have the epsilon, which tells me that R of Sy is equal to y. So concatenating this path and this path, epsilon y, which is a proof of Rsy equals y, I get a proof of Ra0 equals y. So the proof is over because this is for arbitrary y. So I really have that R of A0 is a center. Okay, so now comes the proof which I promised, namely the fact that we can start the hierarchy not with propositions, but with contractible types. So we are going to prove that isprop is built on top of iscontr in the same way that isset is built on top of isprop, or more generally, in the same way as isn-type is built on top of isn-1 type. So we need to prove this. Okay. First thing is we already have at our disposal, we already have proved interesting thing. We have proved that isprop of something is a proposition. Okay, and also that iscontr of something is a proposition. So we know that here we have a proposition. We know that each of these guys is a proposition, is contractible. Okay, but we also have shown. Did we show this? We have that contractible types are stable under. No, okay, but I will state it. So yes, okay, so we know that this. I'm sorry. We know that this guy is a proposition, okay, and we have shown that propositions are stable under the pi construction. So let me go back just to make sure that I'm not cheating with you. Closure of proposition under some type format. So we already proved exactly that if each bx is a proposition, then px bx is a proposition. So we know without any cheating that both types are propositions. This is good. So what we need to do only is to provide functions between them, because we only need to prove logical equivalence. Okay, so in one direction, suppose that I have a proof of this. Okay, then what I need to prove in order for we need to prove a witness that A is a proposition. So we need actually to have a proof that x is equal to y for all x and y. So if we apply d to xy, what we get is a dxy, which is of type iscontr of x equals ay. But this proof is itself a pair of an inhabitant of x equals y and then a proof of something. So if I take the first projection of d of xy, this is a witness that x is equal to y, and this is enough to show isprop A. So this function here does the job. This function is a nice element of isprop A. So I can map D to this function. No problem. Now, in the converse direction, suppose that I have a proof that A is a proposition, and we want to show that this guy is that x equals ay is a contractible. So for this, we know that we have to provide a pair of two things. We have to provide an inhabitant of x equals y and an inhabitant of what do I want to do? Here I wrote something stupid. I want an inhabitant of x equals y, and I want a proof that all the other inhabitants are equal. So forget about this. This is terribly stupid. But what is not stupid is that, okay, I'm not sure what I'm doing here. Let me check. So for the first element, for the first thing that I need, it's easy because C being of type is prop A, if I apply to x, y, I get a proof that x is equal to y. So I provided the first element here. So now what did I say here? Okay, I think this is again stupidities. Well, this stupidities in the sense that it's overly complicated. So for the second part, I will exploit the fact that given that A is a proposition, it's also a set. And this means that, as we have used before, we have used this argument before, being a set means that all the proofs of x equals a, y are equal. So the second component which I'm seeking here holds trivially. So I don't even need to specify it because A is a set. That's the idea. So I will state it more properly tonight, so to clean this slide. Okay, so this is important. We can start the hierarchy at level -2. So now I hope to be able to complete. Yes, I will try to complete, and I will start. No, I will not do that. I will complete these small, well, not small, all these properties of n types next time at the beginning of the course. I prefer to finish in the last 5 minutes, but with a preview of the discussion of equivalence. Okay, so the last 5 minutes will not be technical. I will just give you a plan of things to do. I think it's at this time you are probably tired of technical proof, so it's better to have more something a bit more conceptual. So our goal with the treatment of equivalence here will be to show two other possible definitions of being equivalent. Okay, so I can give them to you now. So we already know Qinf and we know Binf. Now I'm giving you is half equivalence, okay, which is the following. So is half equivalence is like Qinf in the sense that you have a single inverse, you have a proof that it is a left inverse, you have a proof that it is a right inverse, and moreover, you have a relation between these two homotopies, okay? And this is called the coherence condition. So you see that this lives at a dimension just above, okay? So it's called the coherence. So that's another way to define is half an equivalence. It has more information than just being inverse. Okay, it says that the way to show that they are inverse are themselves related. So it's an interesting other type. And the fourth one is of a different flavor. It says that F is an equivalence if for each element of the type B, okay, so you have your F from A to B, and it says that if you take any element of B, and if you take just the fiber here, so take above Y, you have the fiber of F over Y. If you can show that all these fibers are contractible, then you say that F is an equivalence. So what is the intuition? Well, the naive intuition is saying that this is contractible means that actually this is just a point. So it is a function for which the inverse image of each point is a singleton. And if you think for a while, it means that F is a bijection. It's both injective and subjective. Injective because it doesn't contain more than one element, and subjective because it contains at least one element, exactly one element. So this is also a decent way of defining that something is an equivalence. So what is the plan? The plan is, and we will execute the plan tomorrow, is to prove that these four notions that we have seen are all logically equivalent. Okay, so if it is the matter of proving that two types are equivalent, I can use any of them. Okay, but we will show that among those four, this guy is not a proposition and all the others are propositions. So we will show that all of them are propositions. Hence, because they are logically equivalent, they are also equivalent. Okay, and because we formulated univalence with bi-inv, okay, we could as well have formulated it with is HAE or with here I should have written is contre map. Sorry, this is also a typo. Is contre. No, contre. What did I write? Contre map. Okay, here this should be contre map. Okay. So time is more or less over. So then I see you. Bye. See you tomorrow. So did you stop?